Uh, Good morning, everyone. My name is Eric Lombardi, and standing with me is one of my project partners, Scott Wheeler. And today we're excited to discuss with you about how we can use nanotechnology to improve the mechanical properties of compostable films for use in grocery and retail applications. So what I want to contextualize the problem that we're trying to solve. So today, the prevalence of plastic bags is ubiquitous. 1 trillion plastic bags are used for grocery and retail in the world, 80% of which is in North America and Western Europe. In Canada alone, we use 2.8 billion plastic bags every year, and in the Toronto area, that number is 476 million. That's almost 7,000 cubic meters of plastic waste being produced in Toronto alone every year, all of which can take thousands of years to degrade. And now I'm sure you're thinking to yourself, well, what about reusable bag options? Well, when it comes to waste, that would be a correct assumption that a reusable bag will reduce the overall amount of waste. However, when it comes to the actual processing and manufacturing of reusable bags, you will actually have to use that bag over 130 times before it has the same carbon footprint as a regular HDPE bag that is used for grocery and retail. So, I mean, it's less waste, but is that really the best we can do when it comes to the environment? We don't think so. In fact, we believe that compostable is the best alternative solution to traditional plastics used in plastic bags in retail and grocery. This is because the standard requirements required full degradation of these bags within 90 days in a proper compost processing plant, so 45 degrees Celsius with churn. So that is much faster than the thousands of years that you get for plastic bags. Moreover, this is a great time to start looking at these things because consumers are becoming more aware of the impact of plastics and governments are starting to take action. We see in Italy, they were the first country to ban plastic bags back in 2014. In France, they've banned all single-use cutlery and utensils. They're also implementing a plastic bag ban. And just to the south of us, the largest state, California, voted last November on a ballot proposition to ban the use of plastic bags for grocery. Closer to home, Montreal has a plastic bag ban starting in 2018. But if you look closely, the bag requirements are less than 50 micrometers. And so what is largely going to happen is thicker plastic bags are going to be sold, and the incentive here is to promote the reuse of these bags. And I actually have a bag that's going to be used in PC stores in Brosseau, Quebec, which is just north of Montreal. And you can tell how much more plastic is being used just in that alone. So it's questionable about whether or not this will prevent more waste from going to landfill. So this might be leaving you with the question, why don't we see compostable bags already? Why are they not here? I mean, many of us participate in municipal green bin programs. Many of us buy compostable bags. There's already a market for it. Well, there's 3 major barriers to the use of compostable solutions. The first is their cost, which is becoming more economically competitive as governments take action. The second is weak mechanical properties related to tensile elongation and tear. And then finally, poor barrier properties. I am sure I'm not the only one who has taken a compostable bag from their kitchen and frantically ran to the garage because it was wet and starting to drip. I'm sure that has happened to many of us. So there's an opportunity here. In Toronto alone, 240 bags are used every year by each household, and 71% of households participate in green bin programs. So if Torontonians went compostable, $15.4 million in savings could be achieved for families who participate in green bin programs. 2,700 tons of waste can be spared from the landfill, and the total market approaches $50 million for this application. So with all of this in mind, we've created 3 major objectives for our project. And these objectives are to A, and as I said before, improve the mechanical properties so that they can be used by retail and grocery applications without sacrificing too many characteristics that they currently like about plastic alternatives. The second is to ensure that our process is continues to be manufacturable, that this can be produced with current equipment that is used to produce bags. And finally, we want to reduce the amount of material used per bag because that both lowers the cost for material and the cost for shipping, and the overall impact of each bag is going to be lower. And with that, I'll let Scott take over and discuss with you a little bit more about our engineering requirements.
So the solution we came upon to creating stronger plastic bags is to create a composite material using a base resin of a compostable plastic bag material currently on the market, one of which is the samples I gave to you, and then adding a filler to these, which is either going to be a nanoparticle, which is more spherical in shape, or a nanofibril, which is very long. So the biggest difference between these two ends up being manufacturability, as both of these increase the mechanical properties and barrier properties of bags. So essentially all plastic bags produced today are created on a film blowing line. So this involves melting the plastic, blowing it into a bubble, and then collecting it onto a roll. The problem here is if you have fibers inside of the matrix, these do not elongate and stretch as the plastic is being blown into the bubble and concentrate stress at the ends and lead to tears. So these cannot be manufactured, so this is not a viable option. Nanoparticles, on the other hand, do work pretty well with this process, so we ended up deciding on using EcoSphere. This is a nanoparticle, or a biopolymer nanoparticle, that is created out of maize starch out of Guelph. A few of the good properties is that it increases the strength as we incorporate it into the matrix. It induces crystallinity as it acts as a nucleation point, and it is compatible with matrix resins. So we also had to decide which matrices to use around these. So we had two initial base polymer plastics that we were going to use. The first is EcoVio, which is a blend of polybutyrate and a little bit of polylactic acid to give it some extra mechanical properties. And the second is a thermoplastic starch called Matterby. So to actually bring these from an idea to a final prototype, what we did is first we blended these polymers, and then we tested the mechanical properties of injection molded bars. From this, we chose the best potential candidate to go to a manufacturing facility and blow these into a film. After that, we analyzed and tested the films and figured out how we could improve this for a second prototype, and then from there, analyzed those and concluded what further processes we could work on. So compounding the resin works by mixing melted polymer and filler with whatever content we want in an extruder. So the extruder we used has two screws that act to add shear force to the melted mixture to help break up aggregated clumps of our nanoparticle. This operated at 65 degrees Celsius and extruded a nice tube of our resin that we chopped up and then brought to our manufacturing line to film blow. So after injection molding these into tensile samples, this is an EcoVio, which is a PBAT blend. You guys do not have a sample of this, as when we tested this in the tensile bars, it did not have significant increases in its tensile properties. As a brief overview, you can see there are two regimes here. The first is the elastic region, so this is where you want to design your plastics in, where it's going to be stretched and it's going to return to its original length and you won't get any degradation of properties. The second region is the plastic region. And you can see in the plastic region, adding EcoSphere significantly decreased the elongation at break, but this is unimportant because if your plastic bag starts stretching more than 20%, you can't use it because it's going to be dragging on the ground. From this, we concluded that EcoSphere did not properly blend with our filler, so it was not a viable option moving forward. Fortunately, when we mixed Matterby, which is a thermoplastic starch, with our nanoparticle, which is a starch-based molecule, we got a much better result. We ended up with a 20% increase in the stress at break, or stress at yield, and a 170% increase in the tensile modulus. This translates to a bag that, if it's the same thickness, is 20% stronger, or if you have a 20% thinner bag, you have the same strength. So this can directly be translated into savings on material cost. Before we could go and manufacture this in the film blowing line, we needed baseline data on the melt flow properties of our material. So to do this, we just ran a simple melt flow test, and then as we were expected, the more EcoSphere we add, the slower it flows, which means it's a thicker material. So this helped us set the parameters when we were blowing this into a film. The next step is we went to a manufacturing facility, and these are pictures of us blowing our film and the virgin film, the virgin Matterby resin that you both have, that you have samples of both of these. So after this, we brought it back, If you look at your samples, you can see that one is very smooth, where the other one has these well-distributed clumps in it. So those clumps are aggregates of our nanoparticle. So looking at them under a microscope, we could visibly see much better that the ecosphere is still aggregated into particles. It also has smaller particles distributed throughout. So this shows that we did start to distribute the particles, but it was not a completed process. One very good thing is when we looked at images of ecosphere by itself and ecosphere in our resin, it was much smaller and much smoother. So this indicates the forces were starting to act and degrade this, but we need either longer time in the extruder, which is not possible with our current extruder, or higher shear force, which again was not possible with the extruder that was available to us. We did do particle analysis on these microscope images and found that the ecosphere powder by itself is about a normal distribution, about a particle size of 50 micrometer diameter particles, whereas the particles that we found in our blend, the ones that were visible, were much shifted towards a less than 15 micrometer. So this indicates that further processing or further development of the process would greatly increase the material properties and make it a much smoother, better feeling plastic. So to summarize, though the particles were not homogeneously distributed, they were well dispersed throughout our material, which is very good. And we have decided that there are a few possible improvements that could be made for a second prototype. And Eric is going to go into detail on these.
Yeah, so we can see here that potential solutions we've listed are, there's three of them. The first is solvent blending. So this would essentially be us taking our matrix resin, in this case, matter B, and dissolving it in solution with our ecosphere aggregates, blending to ensure that there's a deaggregation of those nanoparticles, and then evaporating the solution out so that we're left with a homogeneous resin. But the amount of solution you would require in order to really do this blend would actually be about 90% of the mass of the total solution to material, and that is just not a scalable process, and we really did want to ensure that our process was manufacturable. So that made us pursue physical chemistry, which is increasing or adding new additives to the material blend in order to increase the shear or reduce the amount of that is required in order to break up the aggregates. So we worked with one of the companies that helped us blow our film called Polymer Specialties International, and they're based out of Newmarket. And they are developing a proprietary blend that uses ecosphere. And they also incorporate a 1% partition agent and a 33% universal carrier. And what the universal carrier does in this blend is just allows the partition agent to be compatible with the ecosphere. The important thing here is that the partition agent has a shape that kind of looks like it's triangular, and so the purpose is on a micro scale to be able to break up those nanoparticle aggregates while they are being extruded. However, we noticed that after we did this, there are still visible aggregates present, even though anecdotally they were a little bit less. Furthermore, we did some testing on the tensile properties of this new blend, and we found that there was not a significant increase in the tensile properties with this new blend that we were using. And we think that might be a result of maybe the partition agent or universal carrier impacting the quality of the film. So really is sort of clear from this that ecosphere on its own has a little bit more potential to help. So this makes us go on to the final kind of solution that we're looking at, which is processing. So in our lab, we have a twin screw extruder that really prioritizes movement of material forward and also the distribution of material. And so if you look at the films on your desk, you'll see that our nanoparticles our particles are very well distributed within the film, but they're not dispersed. And so what we would need to do that is a extruder that has water lobes that does not prioritize moving the material forward. So what this allows is more shear to be pushed at the edges, and because there's less forward motion, the material would stay in there for longer. And so hopefully this type of extruder would allow us to create a more homogeneous film. However, the main problem with that is the cost is about $300,000, and there is no known company in Southern Ontario that had an extruder that we could use in order to create a second prototype. So in order to summarize our project, demand for compostable alternatives to common plastics is increasing and people are becoming more aware. Governments are moving to ban plastic bags, and Compostable offers a solution to retail and to consumers and to government to solve those environmental concerns. Nanocomposite solutions can increase the performance of these composites and to be in line or even better than established plastic counterparts. And our first prototype is a start, but more advances in physical chemistry as well as processing will be necessary. I'm not sure if you guys have taken a tug at the materials that we've provided, but as you can tell, there is a improvement in strength that is tangible. You can feel it.
And feel free to rip them apart and break them. We have tons of samples.
Yeah. So I would also like to take a moment to thank many of the participants in this project. Dr. Leonardo Simone was instrumental in helping us solve different problems in advisory. We also were very lucky that we had 5 corporate partners working with us on this. Interplast Group, which is a corporate owner of W. Ralston, which is based in Brampton, and Haramar, which is based out of Vaughan. Both of W. Ralston and Haramar make compostable bags already for home and business use, and we used their formulations in order to build upon that. And then we'd also like to thank EcoSynthetics for providing us Ecosphere, and Polymer Specialties International, which was incredible for helping us create our prototype, but also gave us a lot of advisory and advice on materials, potential solutions to the problems that we saw with the lack of dispersion, and gave us access to their new thing. So thank you, and please let me know if you have any questions.
Thank you. All right. Any comments or questions? Go ahead.
Why do you think starch can help?
So there are 2 main properties. One is that starch can act as nucleation points to induce crystallinity in the material. A higher crystalline material is more brittle, but it has increased strength as well as better barrier properties to moisture because it's more well arranged. It's a lot more difficult for the water molecules to get through it. Additionally, with any composite materials, if the tensile properties, the tensile properties in general of the composite you're adding into the matrix is better than your matrix itself, it's going to improve. This is the basis of like carbon fiber and glass-loaded polymers that are used across this room. Every single chair here, I bet, is a glass-filled nylon. This is because adding glass to and making it a composite material makes it much stronger.
And these 2 have the same thickness?
It is a lot thinner for the base resin, the virgin matter by, but this is accounted for in all of our stress strain curves. Those are corrected for the cross-section of the material. These are just a representative sample. Because it's a lot thicker, we would need more research done into the manufacturing process needed, and unfortunately we don't have a manufacturing study.
It's likely, when we measured, the matter B film was around 25 microns, and I believe
It was like 15.
And I believe our blended solution was around 40. So.
Yeah, so you focused on using the Ecosphere in your composite. Did you, so what other materials did you, alternatives to Ecosphere, did you?
So the alternatives to Ecosphere that we analyzed were cellulose nanofibers, cellulose nanocrystals, and cellulose microfibrils. Unfortunately, all of these wouldn't survive the film blowing process as their fibers. Exactly.
In terms of other particles, are there any alternatives to Ecosphere?
We did take a look at using clays, but we thought because of their tendency to absorb moisture would be a problem for our product.
Additionally, we did have EcoSynthetics, which was willing to let us test with using their material, and that was extremely beneficial to both access to it and getting information on, okay, so it's in these aggregated clumps, you need higher shear to break them up.
So you said you use industry formulations. How much of choice of filler and polymer is there? Is that their idea, and how much of it is your idea?
So filler and polymer, essentially we were talking to Dr. Simone about this, and we suggested 5% and 10%, whereas from his experience using Ecosphere as a loading content, he suggested that a higher loading is generally more beneficial. None of our industry contacts actually recommended us any filler content, It was more based off of, generally speaking, from Dr. Simone's experience, 10 and 20 are good. And from my experience working with glass-filled polymers, you usually hit 50 or 30%. So edging towards higher is generally better.
Our manufacturing process partners also understood that we would likely be adding an additive, and we actually visited Haramar back in October, I believe, and their processing equipment actually has 4 openings for materials that they actually put in to like the potential to put into their bags, and they actually only use 2 of them, so they actually had space on their manufacturing line to add 2 additional fillers as well. So if we had come up with a successful product, we were looking at potentially manufacturing bags with them, but
the only downside there is we would only be allowed to use their facility if we were running it for a full day, in which we would need about a metric ton of resin, so less possible.
Okay, in the interest of time, we have to move on. Thank you very much.
Thank
All right.
you.